This is the work problems for chemistry 1311 chapter 7. Probably the easiest work problems that you'll do. So just what I'm going to do is go through these, and some of these will not take very long to talk about. Just to remind you that we're talking about periodic properties, which means things that change as you move back and forth across the chart. So we said that, for example, it's a lot dealing with how many valence electrons things have. So things in the first column, for example, like lithium, and the things under that, sodium, potassium, and on down through cesium, those things will have similar chemical properties because they have the same number of electrons in their valence shell. And then when you move to the second and third and fourth columns, it's kind of the same thing. So I'm going to go ahead now and click to the next slide. And we're here already started on these. So what I recommend that you do is grab a periodic chart to do this with, and I have one here also. So what they're asking in this first problem is which atom will be larger, and they're giving us 4 pairs. So if you look at A, it says either magnesium or barium. So if you look at your chart on the second column, magnesium is in the 3rd row or period, and barium's further down in the 6th row. So if you go, so remember, one of our rules was that as you go down the chart, atoms get bigger because you're adding more and more main shells in numbers. So clearly here the barium will be larger because it's further down in the chart. It's lower. And then if you look at C, it's the same thing. For C, we're in the 6th column with, we have carbon at the top, and then silicon is under carbon, and then germanium, and then tin. Sn is tin. That's stannous from Latin. So anyway, you can see if you look at the 6th column there, the Sn thing is way below the silicon, so it's going to be way bigger. It's going to have like 2 more main shells, and as you go out and out and out away from the nucleus, the shells get bigger and bigger and bigger because they have to accommodate more subshells. All right, so for A, barium is larger because it's further down in the chart, and for C, Sn10 is larger than silicon because the same reason it's down further in the chart. Okay, the other two, B and D, are different. So if you'll look at your chart, come all the way down to the 6th period, or row 6, that starts with cesium. Okay, you've come across, we're looking first of all for B. Come across until you get to either the W, which is tungsten, or the hafnium. You can see that the hafnium, HF, comes to the left of the tungsten. Now be careful with this one. You might think that they're going to get bigger as you go from left to right, but they just do the opposite. So they get smaller, and we explained this in the lecture notes. Okay, so this is really the only thing that's kind of hard to understand in this chapter. And we said that the reason for this is because as you go from left to right across the periods, you're adding more and more protons in the nucleus. Well, you know, you say, well, we're also adding more electrons, and that's true. But as we add the electrons in one shell, they're all like next to each other. So they don't get in each other's way, or what we call, they don't shield each other from the charge. So the charge they feel from the nucleus is getting actually larger because you don't have any more electrons that are like between you. So if you add another electron, but it's beside the one you already had, then it doesn't really make any difference. But if you add another proton, it does. You see what I'm saying? So the more protons you add, the more charge there's going to be in the nucleus pulling these things, and so they'll just pull these electrons basically closer and closer. So if you look at B and D, you'll see that in both cases hafnium is to the left of the things that it's paired with. So in part B, hafnium will be larger than tungsten, and in part D, hafnium will be larger than osmium. Okay, so our 2 rules, just to review, as you go down the chart, from top to bottom, they get bigger, and that's pretty easy to see. The other rule is that as you go from right over to the left, they get bigger that way also. So I'm going to click now. So click. So here's the chart. I'm going to go ahead and keep going. So click, and here's your answer, which we've just mentioned this. Let's just go ahead and click again. Number 2, state the 2 main factors that determine atomic size, and we just did that also. So as you come down the chart, the atoms get bigger. And notice it says atomic size. So this would indicate that we have a neutral atom, we don't have an ion. Now the other factor is as you go from right to left across the chart, they get bigger. Okay, next, here's a picture. We've seen this before, and it's very dramatic. As you can see here, moving down the chart in any of the columns will get bigger and bigger. And then moving from right to left, basically you can see a pattern there where they're getting bigger and bigger. You can actually see it more so in the first column and the second column, and then the third column. And then once you get to the fourth and all the way over kind of like to the eighth, it's not really like, I mean, you can see that it isn't going to be a linear thing. And what I mean by linear is, I mean, it's like proportional. So clearly something's going on that's not exactly what we say, but for practical purposes, we can say that as you go from right to left, if you just look at it as a whole, you can see that they're definitely getting bigger. Next slide. All right, so for the next one, it's a little different because we're dealing with ions. So ions are different. So remember the rule for ions. If it's a negative ion, we call it an anion, and it will get bigger because you've got 2 reasons. First of all, you've got more electrons and protons, and secondly, you've got more electrons, so you've got more electron-electron repulsions. So they get considerably bigger. Cations or plus ions get smaller because, number 1, you've got more protons than neutrons, and number 2, in some cases, you're going from a larger shell. In other words, a larger N number to a smaller one. So look at A, it's copper neutral, copper plus, and copper 2 plus. So which one of these is the biggest? Well, it's going to be the one that doesn't have the charge. So that's going to be copper. So actually, the way that that one is written for part A is correct. If you take away 1 electron to make it copper plus, then it will get a lot smaller. And that's because you now have more protons than electrons. And then if you take away another electron to make copper 2 plus, it will be even smaller because now you have 2 more protons than you have electrons. For part B, you'll have to look at your chart for this one. You'll have to find nickel, palladium, and platinum. So let's do that. So let me find it. It's over in the transition metals, so it's going to be in the 10th column, where when I say 10th, I mean when you include the transition metals, it's the 10th. Nickel is at the top, and then it's in order the way it is there. Nickel's in the top, at the top, palladium, and then platinum. They're just in a column. So come over to the 10th column, and nickel's at the top. It's also atomic number 28. And then right below that is palladium, and then right below that is platinum. So the platinum atom is going to be bigger than the palladium atom, and then the palladium atom is going to be bigger than the nickel, right? So that's going to be the same thing for these 3 ions, because they all have the same charge, so it's going to be the same order. They all have the same charge, so the platinum 2 plus will be larger than the palladium 2 plus, which will be larger than the nickel 2 plus, so they're going to go in decreasing size from right to left in B. In C, we're adding electrons, so as for the reasons we mentioned previously, every time you add 1 electron, the atom will get bigger, it will become an anion, and then if you add another electron, it'll get even bigger. So the order of this one going from larger to smaller would be O2 minus, and then O minus, and then O. Next slide. Here are the answers. Next slide. And then just a chart. but this was number 4. Which of the ions Se2 minus, F minus, O2 minus, and rubidium plus has the largest radius? Okay, so to do this problem, let's divide these 4 things into 2 groups of 2. So if you look at selenium, and that's in the 4th row, over at the right, almost to the end of the 4th row, and rubidium is the very first thing in the 5th row, or period. So those 2 things, and let me say them again, it's the Se and the Rb are going to be both, clearly are going to be larger than the other 2 things, right? Why? Because they're so much further down the chart. And so that means that we have 2 things that are on the, like, going to be larger, Se and Rb, and then we have 2 things that are going to be smaller, and that's the F and the O. Do you see that? So let's just talk about, first of all, let's just make a general rule here that the Se and the Rb will both be larger than either the O or the F. So let's now look at the Se and the Rb. The Rb is actually down below Se, but if you take away an electron to make it Rb plus, it will drop back down to the 4th row. In fact, if you take away 1 electron from rubidium, if you look at the chart, it will drop back until it has the same electronic configuration that Kr has. Over in the 8th column in the 4th row, that's krypton. It will have the same configuration, but it will also have a plus charge because now it has more protons than electrons. So it will actually get way smaller than it was before. Selenium, on the other hand, if you add 2 electrons to it, excuse me, it will have also the same configuration as krypton, but it has 2 more electrons than it has protons. So you've got, first of all, you've got more electrons, more negative charges, so that would make it bigger. But then also, these electrons will also repel each other, and that makes it even bigger. While we're on this, I want to just mention that when you have Se2 minus, it's going to have the same configuration as krypton, neutral, and Rb plus will have also the same configuration as krypton. So when 2 things are like that, we say they are isoelectronic. ISO means same. So it means that they're the same configuration. They both have the same configuration as krypton. Now watch for that on the final exam. They always ask this. So they'll give you, like to use another example, if you look up at the 2nd row, where you have OF and Ne at the top right of the chart. If you had, for example, O2 minus, F minus, and Ne neutral, all of those would have the same electronic configuration. So they would be called isoelectronic. Now let's look at the last 2 things here, the F and the O. The F is a minus and the O is 2 minus. So if you look at the 2nd row at the right, F minus would be larger than F because it has more electrons and protons, and it also has the extra electronic repulsions. But O2 minus has 2 more electrons and protons, and also it has more electronic repulsions. So which of those 2 do you think would be bigger? And you can make the argument that F minus also has 1 more proton, but it turns out that the main factor that determines this is the fact that O has 2 extra electrons. So the O2 minus would actually be larger than the F minus. Okay, and then the next slide, which I'm going to click to now, will show all 4 of these. Okay, so you can see here they're all in order. So Se2 minus, Rb plus, O2 minus, and F minus, and I'm reading from the very bottom of this slide. Click. Okay, number 5, ionization potential. Explain the periodicity involved with this. Is that it is easier to remove an electron from something in the first column, or the first group, which we call the alkali metals. So anything in the first column, the electron will come off quite easily, or in other words, you don't have to put much energy into it to get that electron to come off. Do you understand that? So, and then the second column, well, it will be a little bit harder, and it's actually going to be harder than we expect, because when you have two electrons in something, you have a filled s suborbital, which means it's kind of stable, but not as stable as an octet, but it has some stability. So it's going to be a little harder than we would have anticipated. So if we look at a graph of this, when we get to the second thing in the column, when we look at the second thing in the row, then it will be a little harder to remove that electron than we would have expected. And we will look at a chart in just a moment. Then basically it picks up again from 3 to 8, with one other exception, which we'll talk about in just a minute. Then it gets harder and harder and harder to remove that outer electron. So by the time you get to the 7th column, it's real hard, because F in the second row, F is in the 7th column, and it's very, very difficult to remove an electron from F, because it has already 7 and it really, really wants one more. And then the hardest ones to remove are the ones in the 8th or noble gas column. Okay, so I'm going to click, and I'm going to click again. Now, this chart is really the best thing to look at to study this, and you want to just focus on the things from the, so if you'll, okay, go to the far left, and you can see all these like violet or purple colored dots, right? Come all the way to the left to the y-axis, and you see hydrogen at about 1300, and then you see helium above it at about 2400, right? And then come down to 500, do the third thing. Okay, that's going to be lithium, and I'm going to read the next 8. I'm just going to read them off the top of my head. It's lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, just focus on those right now. In fact, permanently, because the other rows, as you keep going to the right, they get more and more confusing. So I would just focus on everything from element number 3 all the way up to element number 10. So let's just look at that one section, which I would point it out to you if I could, but the marker doesn't work. It works, but then what happens is it will show everything I marked at the end of the slide at the beginning when I redo it, when I save it, so it's just useless. So let's just start at the bottom. So the thing at 500 is going to be lithium. So you can see that it only takes 500 kilojoules per mole to remove its outer electron. Whereas when you move up to the next one, that's going to be beryllium. Well, beryllium has a filled s subshell, so it's a little harder. You can see it's almost at like 900. I don't know if you can see what I'm trying to say here, but it's harder than the next one, which is weird, right? But it shouldn't be, right? It should be linear, but it isn't. And the reason is, in other words, this beryllium is harder to remove its outermost electron than the next thing, which is boron. And the reason is because beryllium has a filled s suborbital, and to remove that one electron that you're trying to remove right there, it would be destroying that filled s suborbital, which it doesn't want that. So you have to work a little bit harder. Then when you get to boron, boron has 2s2 and then it has 2p1. Well, 2p1, that's nothing, right? So you go back down to a lower energy, about 750, because it's not a filled subshell, right? It's just a 1 electron. But when you get up to, boron, carbon, so when you get to nitrogen, so if you'll count from the bottom at 500, 1, 2, 3, 4, 5, then you have another thing that's like up too high. That's nitrogen. So it's the 1, 2, 3, 4, 5th thing in that one row there. So lithium, beryllium, boron, carbon, and then nitrogen. You notice nitrogen is higher than the thing right next and below it, which is oxygen. The reason is because nitrogen has a half-filled suborbital. It has 3 electrons after the s, so it has 1s1, 1s2. I'm sorry, 2s1, 2s2, and then it has 2p1, 2p2, 2p3. So the total amount of electrons that p's can hold is 6. So when it has 3, it's half full, and that has a certain amount of stability, just like a s suborbital that's full. And what that means is that that third electron, in other words, for nitrogen, it's a little bit harder to remove than we would have expected it to be. So just to kind of review this a little bit, the most stable configuration here is going to be an octet, and you see that in neon, which is all the way at the top there, around 2000 or 2100. And then we have 2 other things that we could consider to be anomalies, nitrogen and beryllium, and the reason they're harder to remove is because in the case of nitrogen it has a half full p suborbital, and in the case of beryllium it has a full s suborbital. Now another thing is that when you get all the way to the top there with neon, it has an octet, and if you think about it, it also has a full p suborbital, right? But so I mean it doesn't really make any difference for neon, because neon is an octet, which is the highest you can get. So that is the thing that we need to know about this. So for a test, what you can expect to see would be some question that is asking you, for example, why is it harder to remove an electron from beryllium than from boron? And the answer is because it's got a full s suborbital. Or another thing would be, why is it harder to remove an electron from nitrogen than from oxygen? Again, same answer, except that in this case it's because nitrogen has a half full suborbital, a half full p suborbital. I'm going to go to the next slide, so click. All right, so state the general principles in electron affinity. Now this is not what we've just been talking about. Electron affinity is only the amount of energy that is given off when you drop an electron into an atom. So the only atoms that really want another electron are basically the things in the 7th column or group, the things that we call halogens. And to a lesser extent, that's true of things in the 6th column, like oxygen. So they also want another electron, but they don't want it quite as much as things in the 7th column. And things in the 5th column may or may not want another electron, because, as we just said, things in the 5th column have a half full p suborbital, so they're already fairly stable. But so in some of the periods you'll see that they do have an electron affinity, and others they'll have a 0 electron affinity. So what electron affinity is it's the amount of energy that's actually, in this case, it's actually the energy that's released. So, for example, fluorine will actually give off energy when it becomes F minus, because F minus is more stable than F. And then if you keep going down the chart, Cl minus is more stable than Cl neutral. And so it's another way of saying what we just said, that if you throw an electron at an F atom that's neutral, it will grab it and it will turn into F minus, and F minus is more stable than F neutral, which means it's lower in energy, so the energy is given off. And so they measure that. I'm going to click to the next slide. So here we have another chart like the one we just looked at. But the difference for this one, again, we're talking here about electron affinity. So the difference in this one is that if you look, these are measured, first of all, on the y-axis. We've got negative values. So the higher you go up on the y-axis, the more energy is given off. In other words, the more they're going to become more stable as you give them an extra electron. So, but notice here, the only things it really affects are the things in the 7th column, mainly, and then things in the 6th column to a lesser extent. So if you look at F, these actually have these marked. There are 4, like right across the top there, F, Cl, Br, and I. Okay, these are all things in the 7th column, and they're above minus 300. Each of them is right at or above minus 300. So that means that they really, really want one more electron. And then if you come down to the next like wave there, you've got oxygen, and then these are not marked, but whatever's before chlorine, whatever's before bromine, and whatever's before iodine, that second row of things that are all around minus 200, these are the things that are in the 6th column or group. So these also give off some substantial amount of energy, but not as much clearly as the things in the 7th column, but still a significant amount, so about 200 kilojoules per mole. Okay, now notice what happens when you come to the next row. In the case of the 2 down, before you get to FO, so that would be nitrogen, it's 0. And again, the reason it's 0 is because nitrogen's pretty happy just to have the 3 p orbital electrons, because it's half full. And then phosphorus would be the next thing under that in the chart. And if you look at phosphorus, it's not 0, but it's not that high. It's less than 100. So what can we conclude about this, and what can you likely expect to see on the test? That the only things that really matter with electron affinity are going to be things basically in the 7th column or group 7, and then things in the 6th column or group 6A, would be also less important. And then in the case of group 5, those vary. So the basic summary we can make for this is that it's mainly things in the 7th column and then to a lesser extent in the 6th column. Now you wouldn't need to know this, what I'm going to say now for the test, but in the old days, the way that they figured out something called electronegativity, which you'll have to be careful not to confuse with electron affinity. Electronegativity is much more important and something that's used a lot more than either of the things that we just mentioned, okay? So, and we don't talk about that until we get to chapter 8, at the beginning of chapter 8. The electronegativity used to be calculated by averaging the absolute value of this electron affinity with the ionization energy. So, and you can still get a rough idea by doing it that way. They don't do it that way anymore. But just keep that in mind. Okay, so let's go ahead and click to the next slide. So which of these elements, so take a look at this. We've got beryllium, which is in the 2nd column. Nitrogen is in the 5th, oxygen is in the 6th, and F is in the 7th. Well, we just talked about this, right? So which one do you think is going to have the most negative electron affinity? So I'll let you think about that for a second. Okay, so hopefully you decided on F, because F is in the 7th column or group, so it's going to be the one that will be most likely to get another electron and give off more energy. Which one would be second most? Well, it would be O, right? And then N and BE are both at 0. You wouldn't really be wrong if you chose N if you were asked for the third most. But if you look back at that previous slide, which I can't go back because of the way this slideshow is set up, you can't go back. But if you look, you'll see that N and BE are both at 0. So, I mean, and clearly beryllium is trying to get rid of electrons, not gain them. So the only one that you're likely to see, the only way you're likely to see this on a test would be the way it's stated right here, where they ask you which one of these 4 would be most negative. So your answer is going to be F. I'm going to click to the next slide, and then I'm going to click again. Okay, number 8, consider the following ionization energies for aluminum. So before you start this, if you've got a chart, if you look at it, you'll see aluminum is underneath boron. It's in, well, it's under boron. So it's in 3A, or column 3. And the main point of it is that it has 3 valence electrons. And so this is kind of a new element that we haven't really talked about that much. But consider it just to kind of be like boron in some ways. So aluminum would have 3 electrons in its valence shell. So if you don't see that, just count over. So you're counting from sodium in that case, right? Na, sodium. So Na and then Mg. So that's 1 in Na, 2 in Mg, and 3 in aluminum. 3 valence electrons in aluminum. So is it easier for it to get rid of 3 and go to Al3+, or is it easier for it to gain 5 and go to Al8, 5-? It's easier for it to give up 3. So that's what it does. Like all metals, it gives up electrons rather than to gain. So notice here they're showing us what happens if it gives up 1 and then 2 and then 3, and then it shows us what happens if it tries to give up more than 3. So for 1, it's 580 kilojoules per mole. For 2, it goes up quite a bit to 1800. For 3, it goes up again quite a bit to 2700. But look at the drastic difference between 3 and 4. So part A down at the bottom, account for the trend. Well, to remove 1 electron isn't that bad. So I1 is only 580. And then not that bad to remove the second one, right? But more than the first, because now you have aluminum plus that you're trying to remove the electron from. So that means you've already got a situation where you've got more protons than electrons. So it's going to hold on a little harder, a little tighter. And then once you try to remove the third one, yeah, it's going to get harder and harder. And it's just common sense that every time you try to remove one more electron, it gets harder and harder. So, I mean, while I'm thinking about it, just to kind of break the monotony here, when we get to the chapter, if you take 1412, when we get to the chapter on nuclear chemistry, which is the last chapter we do, we talk about how to measure the mass of a nucleus. And I'll come back and I'll finish this problem in just a moment. So imagine you've got a gigantic nucleus like uranium, which is over around 100 protons. Can you imagine how difficult it would be to remove all 100 electrons from a uranium atom? And yet we need to know what the mass of the uranium nucleus is to do some of the problems in that chapter. So there's a trick to that, which we'll talk about if you take 1412. Okay, so to come back to this problem, we have a gigantic increase between 3 and 4. And the reason, if you'll look at your chart, you'll see that once you start to remove the 4th electron, let me get my chart out here, you're actually trying to get aluminum to go all the way back to the neon configuration. So be sure you see that. So grab a chart and count off, trying to remove 4 electrons from aluminum. Okay, if you do that, you'll see that you're trying to take it all the way back to neon, and then you're trying to remove an electron from neon. Well, we've already said that, right? That you can hardly do that because neon has an octet configuration and it really doesn't want to give up any electrons. So not only for the 4th electron here, I4, not only are you trying to remove an electron when you've already removed 3, so you've got already 3 more protons than electrons, but you're also trying to remove an octet electron. So that's why the difference between 3 and 4 is much larger than the difference between 1 and 2 or 2 and 3. Click to the next slide. Next slide. Sorry, I forgot to say click before I clicked that one. All right, so number 8 from Mr. Mack's website. Number 8, in which set of elements would all members be expected to have very similar chemical properties? Well, it's any of these 5 choices that are all in the same column or group. And so we don't really need to spend a lot of time on this. You can just look at your chart, and if you'll look at answer choice B, as in boy, O, S, and Se, oxygen, sulfur, and selenium are all in the same group or column, right on top of each other. So that's going to be our answer. So if you get this on a test or on the final, you're looking for three things that are all in the same column. And if you look at the other answer choices, none of those fit that. So the answer here is going to be B. I'm going to click twice now. Click once to go to the answer and then once to go to the next slide. So I'm going to click again. Okay, number 9, atomic radius generally increases as we move. So we've already talked about this several times. Atomic radius will increase as we go down the chart. So the first thing we can do is eliminate everything that says up a group, like answer choice A says up a group, and C also. So those are out. So it has to be either B, D, or E. And then also the size increases what? What's the other direction? Is it left to right or right to left? And the answer is it's from right to left. So if you look at answer choice D, it's down a group and from right to left. Okay, and I think we've talked about this enough. I'm going to click to the next slide and then the next one. So I'm going to click again on this one. Number 10, the atomic radius generally increases down a group because, so now they're saying why does it get bigger as you go down the chart? And the answer is B. The principal quantum number increases. In other words, what that means is that every time we go down a group, every row has one more layer of electrons on it, if you want to think of it that way. So if you go from 1 to 2, or 2 to 3, or 3 to 4, or whatever, every time you go down one row, you're making the atoms much larger because you're adding a whole new shell and a whole new N number. And remember, every time you come down a row, you're also adding in other words, every new row can have one more subshell. So the first row can only have S. The second row can have S, but it can also have P. The third row can have S, P, and then D. But you don't see the 10D things there in the third row, and the reason is because they're put into that chart the way they actually feel in nature, not the way we would maybe like them to be. I mean, you could put them in the third row, and that would be theoretically the way they should go, but they don't feel that way in nature. When we get to the fourth row, we can have S, P, D, and then we can also have F. So if you look at the chart, the F things are all the way at the bottom, the actinides and the lanthanides. So they're not even really placed into the chart itself. They're kind of listed separately because we don't really use them that much in chemistry, at least at this level. Next slide. Next slide. 11, screening by core electrons and atoms is, why don't you take a look at these for just a second? Okay, so the answer choice is A, more efficient than that of valence electrons. And that's actually the correct answer, because the valence electrons don't screen the other valence electrons at all. Because if you think of it like this, think of it, you're standing out in the yard and somebody else is like, you know, your friend is standing right next to you. Well, are you shielding your friend from the sun? I mean, assume it's in the daytime. And I mean, the answer is no. If you got 10 people out there, you're all standing right next to each other, none of you are shading each other from the sun. I mean, you might be throwing a little bit of shade depending on what time it is, but let's just say it's high noon, sun directly overhead, you're all standing in a kind of a circle, the sun's going to hit all of you the same way. And that's what they mean here. So valence electrons are the same way. They don't shield each other from that charge that's in the nucleus. So what they mean by core electrons, C-O-R-E, are the electrons that are in interior shells. So they will screen the ones that are in the most outer shell. So their screening is going to be more efficient than that of valence electrons. You can look over these other answers. They're all wrong. Click to the next slide. Click. Consider the following electronic configuration to answer the questions that follow. I only took one of these. So we've got, for answer choice 1, we've got 5s1, 2 is 3s2, 3p5. So that means here for choice 2, we've got 7 valence electrons. Choice 3, we have 3d10, 4s2, 3d10, 4p4, so we have 4 valence electrons. Choice 4, 3s2, 3p6, we have an octet. In choice 5, we have 1 valence electron. So the question is the electron configuration of the atom that is expected to have the highest first energy, ionization energy is question mark blank. We're looking for one that has an octet. That's what we should be looking at before we even start looking at the answer choices. We want something that has an octet because those are the hardest to remove electrons from. So in other words, that's another way of saying they're going to have the highest first ionization energy. Okay, so do any of these 5 choices have an octet? And the answer is yes, one of them does. It's 4. So that's going to be our answer, D. So that's what you would choose. Now, what if there were not any that had an octet? So why don't we just imagine that answer choice D has been removed, and we have to choose from the other 4, then which one would you choose? 1, 2, 3, or 5? And the answer would be 2, right, because it has 7 valence electrons, which means it's in the 7th column, or it's a halogen, so it's going to be like, in this case, it's going to be chlorine, which means that it really wants 1 more electron. So what they're asking is which one would be the hardest one to remove an electron from, and it would be 2 in that case, because it's going to really hold on to the electrons that it has. It wants 1 more. Click. Click. Blank have the lowest first ionization energies. Which group has the easiest outer electron to remove? And that's clearly going to be things in the first group. So all we have to do is remember the name of that. So we call things in the first group or column alkali metals. And it's easy to get this mixed up. Alkali metals are the first column, alkaline earth metals are the second column. It's very easy to confuse these, so be careful, because you could know the answer to this and still miss it. So the way that I remember it is it's the thing that has only alkali metals first in the first column, and then the second column you have to add a second word to the alkaline, so the second column is alkaline earth. If you can remember that right now, believe me, it'll save you a lot of trouble all the way through organic chemistry and any other chemistry you ever take. The second part down at the bottom, which of the following has the largest second ionization energy? In other words, what they're asking here is which one of these things would be pretty easy to remove 1 electron from, but not another one. And that's going to be something in the first column or group, which is the same group we just had above, right? It's the alkali metals. The reason is because, like, if you look, it's answer choice D. Sodium's in the first column, so 1 electron will come off pretty easily, but after that, no. You see what I'm saying? So, like, anything in the first column wants to give up 1 electron, but not another one, because once it gives up that 1, it attains a stable octet in the row before it. So let me just look this up real quick, but sodium is going to attain the same configuration as neon. In other words, it's going to have an octet. It's going to be isoelectronic with neon. So the answer is going to be D, sodium. Next. Next. Now back to what we said before, things that are isoelectronic. So things that are isoelectronic, that means they have the same electronic configuration. So we're looking for some combination of three things that have the same configuration. Now C, answer choice C is in cat, can't, because you're going to have one thing at least that has a charge. In fact, you're going to have two things that have a charge. I suppose it's possible you could have three things that have a charge, but probably, and so A is out too. You can't have they can't have the same configuration if they're different elements. So A's out, C's out. So let's take a look at B. So on your chart, if F had one more electron, it would move over to neon, and then the other one there, Na, if you look at Na, if you take away an electron from Na, then it would also have the same configuration as neon, right? And then we've got neon. So clearly here the answer is going to be B. Because if you do this the way they have it set up, they're all going to have the same electronic configuration. If you want to take a look on your own at D and E to see why they don't work, that would be a good exercise. Okay, so but the answer is B. Next, click, click, and that's it. Okay, so I went longer than I anticipated, but that usually is what happens. But hopefully this will be helpful to you. So I'll go ahead and get these posted, and you'll have them available for next week.